linked list in parts, which is Leetcode 725. The question is here as follows. So you're given a head of a singly linked list and an integer k. So you're supposed to split the linked list into k consecutive linked list parts and return all the new heads of the newly divided linked list in a new array. So what this means is that, let's say if your linked list, right, has 10 nodes, starting from, let's say, 1 to all the way to 10, right, and let's say your integer is k, which means that you need to divide these 10 nodes into two buckets. Each bucket would have five nodes in it. So the first bucket will have node 1, which points to 2 to 3 to 4 to 5, and then 5 points to null, because that's the end of the first sublist. And then the second bucket would have its head at node 6, and it would point from 6 to 7 to 8 to 9 to 10, and 10 points to none as usual. Here are the conditions for the split. The length of each part should be as equal as possible, and no two parts should have a size which differs by more than 1. So what this means is that the maximum size difference between any two buckets is 1. So let's say in the example, right, our example was 5 and 5, so we have 5 and 5, so the difference is just, it's 0. The both buckets are the same size, so it passes the rule. Another case is, let's say we have 9 nodes, right? Then you can, in your first in the bucket on the left, you can have 5 nodes. In the bucket on the right, you have 4 nodes, but the difference is 1, so it's okay. But you cannot have the case where, let's say you have 10 total nodes, you have 6 in the first bucket and 4 in the second bucket. This kind of fails this rule, as the size difference is 2, so we cannot do that. The other thing is that the parts must be in the order of occurrence in the input list, and parts occurring earlier should have a size greater than or equal to parts occurring later. The second part has already been explained previously. The first part means that you cannot skip or reorder the nodes from the original order in the linked list. So let's say it was 1, 2, 3, 4, 5, then you can't have 1, 2, 3, 6, 4, 5, for example, because that's not the original order. So you return the array of the k parts at the end of your program. So the result required is an array of k sub-linked lists, and the size of the sub-linked list must be in decreasing order, and the maximum difference in size must be 1. So it could be 0 or it could be 1. So firstly, how do we determine the number of nodes in each sublist, in each bucket, pretty much, right? So assume that the following array contains k buckets. K in this case is 5, because there are 5 different buckets, and we need 5 separate sub-linked lists. And we need to put a certain quantity of nodes in each bucket, right? First, we need to count the number of nodes in the linked list to decide how to split them into buckets. So let's say count is 22, which means you have 22 total nodes in the original linked list, right? What is the best way to put these 22 nodes across the 5 buckets? Given that the number of nodes should go in a decreasing order from left to right, we can greedily add quantities from the left. What this means is that this will kind of ensure that whatever is on the left is always greater than whatever is on the right, like quantity wise. So the first thing you can do is find the maximum amount you can put in each bucket. So let's say if the total number is 22, right, which means that we can put 4 in each bucket, and that's the maximum amount that you can put in each bucket without exceeding the total sum count of the length of the linked list. So we put 4. This can be derived from 22 divided by 4, which gives a quotient, 2 divided by 5, which is k, which gives the quotient of 4. We still have 2 remaining, and the cool thing about it is that since 2 is lesser than 5, which means it's not going to overflow the length of k, so we can safely add 1 node each from left to right. This will also ensure that we do not beat the requirement that the difference in sizes must be a maximum of 1, right? So The decreasing order will be followed using this approach. So in this case, you can see that we had two as a remainder to begin with. So we add from left to right. So 4 becomes 5, 4 becomes 5 again, and then we have no more remainder to add. So we leave the rest of the sublist lengths as they are. So essentially, we will have two sublists of size 5 and then 3 sublists of size 4. So let's see the approach to decide the bucket counts. First, what we do, we initialize a count variable and set it to be 0, and we have a temp variable which we set it to be the head of the current linked list, which is the initial linked list. So essentially the first for loop does is that we are pretty much counting how many nodes are there in the linked list. So ct plus equals to 1, and then we move temp to temp.next, so until like temp is not none. So then at the end of the day, we will get the number of nodes in the linked list. And then we calculate the quotient, which is ct divided by k, and we get the quotient, and remainder ct remainder k. We also initialize a counts array, which is what we needed to create here, and for I in range k, because k is the length of the case, how many buckets are required, right? So yeah, so we do that, and then if to add, which is how much additional numbers you need to add. So let's say you need to add 1 here, right? So we initially set it to 0. With the remaining amount, is greater than 0, which means we need to add 1 to it, right? So 4 becomes 5. After that, remainder minus equals to 1, as we are already adding 1 to that element in the array. At the end of the day, we append to add and quotient to counts, and we will get this array at the end. Okay, so how do we populate the result array, right? Which is what we need to return for this question. So notice that we already have the counts required in each bucket. We need to iterate through the linked list and break off when the length is hit. So we go through the linked list, and then when the 5th element is hit, then we know that the first bucket has been filled up, and then we move on to the second bucket, right? We make sure that the next attribute of the last node in the end of the first sublist is set to none when we reach the end of the current iteration. So let's see that in action in this code. So this is a main for loop to populate the result array. So we have our counts array, so we have to iterate through the counts to decide how many nodes should be in the current bucket, right? So we create a variable called nhSaved, which is a new head saved, and we initialize it to be the current head, and then we also have new head, which is going to be head. Notice that in the result array, right, we are appending new nhSaved, as that will be the new head of the sublist. Now we have a for loop here, which is for x in range counts I minus 1. Note, you need to realize why it's counts I minus 1, as let's say if you have a linked list of 3 elements in it, right? How many times do you need to go through the linked list? There are only 2 gaps, or like 2 arrows pointing to the right in the linked list, so it's only going to be 2 times. That's why we need to set counts I, the range to be until counts I minus 1. And notice that for each time that we are trying to add an element to the new head, so we set it such that new head equals to new head.next and head equals to head.next. So we pretty much move both new head and head pointers. And at the end of the for loop, which is for x in range counts I minus 1, notice that we would have reached the end of the current sublist. So if it's 5, we would have stopped at the 5th element, right? And we notice that we need to go on and create further sublists, which is why that if there's a head, you set head equals to head.next. Alright, so this is to like assist in like the future addition of the new sublist after this. So after that is done, then if there's a new head, then new head.next equals to none. We need to do that because if you realize it's because the current sublist has already ended, and let's say it's already fifth element or five elements, right? It's already ended, so we should not point it to anything else because the original head points to the sixth element, which is no longer part of this sub linked list. So I point it to none, right? So after this is done, then we can append our new head saved to our result array, and at the end of the bigger for loop here, we will see that our result array is populated with the new heads of the sublist. So let's analyze the time complexity and the space complexity of this question. So for time complexity, notice that we do iterate through the array like a few times, like 3 times to be in fact. But the thing is, we're not going through an element more than once in each iteration, right? So it's still going to be O of n, where n is the length of the linked list. And for additional space complexity, notice that in this case we are storing new head of new heads of the sub linked list as nh saved, as you can see in the example below. And the quantity of these such new nh saved is going to be k, right? Because there are k elements in the counts array. So at the end of the day, we are going to need to have k heads. So this require like a space complexity of OK, as we have k new heads of new sublists created. So that's the end of today's question. Thanks for watching.